All right, let's look at the proof of exponential rule for derivative. Right, so as we know that the derivative of e to the x is e to the x, so it doesn't change at all. All right, so here's the useful property of number e. Right, so here's the limit. The limit of e to the h minus 1 all over h as h approaches 0 is equal to 1. Right? Seems like a random limit, but this is actually the derivative of the exponential function at x equals 0. So geometrically, this is what it means. Right? So f of x is e to the x, so you have this purple curve. This is the graph of exponential function e to the x. And if you look at the tangent line to the graph of e to the x at the x equals 0, which is this red line, and the slope of that tangent line is exactly equal to 1. Right? And I'll show you how you got to this the limit. All right, so if you want to find the slope, we need to take the derivative, right? So you have f prime, and we want a derivative at 0, right? So if you like, use the definition with h, right? Limit as h approaches 0, right? Then you have f of 0 plus h, so e to the 0 plus h minus e to the 0 all over h. So this is just a definition, right? But if you simplify this, you know that you get exactly the limit that we're looking at, right? So you have, there's no point of writing 0, so you can write e to the h minus e to the 0 is 1 and all over h, right? So you can see that this is actually the derivative of exponential function evaluated at 0, which is this left-hand side of the property, right? So we chose this specific number e. Remember that the e is about 2.7 something something, right? So kind of a strange number, but we chose e specifically so that the derivative of that function e to the x at x equals 0 is exactly equal to 1, right? So that's one of the useful properties of a number e, right? So I'm going to use this I'll take that for granted and then try to write a proof for the exponential rule. All right, so proof. So we're talking about derivative. So let's try to find a derivative. So e to the x prime, right? So I'm going to use the limit definition as h approaches 0, right? So you have e to the x plus h minus original function e to the x all over h, right? And using the exponential rule, exponential property, we can split this exponential expression as e to the x times e to the h, right? So which means that we have a common factor on the numerator. So let's pull that out. So common factor in this case would be e to the x. So both of these terms on top has e to the x in it. All right, so you have e to the h. And if you pull e to the x from e to the x, you get 1 all over h. All right. And since limit is in terms of h, so e to the x is considered to be a constant because it has nothing to do with h. So you can place it in front of the limit. Right? So we're going to put e to the x outside. Then we just have to worry about evaluating this limit of e to the h minus 1 over h as h approaches 0. Right? Now you can see where the property comes in. Right? So this is the limit that we just talked about, and this is exactly equal to 1. So therefore, you have e to the x times 1 is, of course, e to the x, right? So this will verify this exponential rule for derivative, right? That's it. I hope that this was clear.